Hello everyone and welcome to the 181 video on gradient descent. Gradient descent is a numerical technique that we use to optimize functions, and we'll be using it in the next couple of videos. I've decided to give it its own video so that we can go over the mathematical technique first, and that way when we put everything together, hopefully it'll be a little bit less confusing. So our motivating question for today is, what if our loss function is not convex? Or what if it's kind of complicated? In linear regression, we've been able to easily solve analytically for the w, and we know that this is the global optima of the function because the function is convex. But in the future, we're going to run into loss functions that aren't necessarily convex, and also we may run into functions where it might be kind of difficult to solve analytically for the w. And so in this case, we need some sort of technique for approximating what is the best w, or finding that through some sort of numerical technique as opposed to just solving for it mathematically. And this is where gradient descent comes in. So we may not know exactly where the best point is, but in gradient descent, our idea is to start at some random point, and then the gradient tells us which direction locally is the quote-unquote best to move in. And what I mean by that is that the negative gradient points us in the direction of steepest descent. And so if we move in that direction, presumably we'll be moving towards a minimum, and that's what we want to find. So mathematically what we're going to be doing here is we will go through in a bunch of sort of time steps, and at each step we have some value of w. Our initial value of w is just going to be some random thing that we pick, and then we're going to subtract eta, which is a learning rate. And I'll talk a little bit more about that in the future, but you can just think of it as a coefficient for now, times the gradient of the loss function at that point. And that's going to give us our new w, and then we'll plug that in and we'll move in another step. And so basically at each step we're just taking our current value and we're moving a little bit in the direction of the gradient. So I've drawn this out above. This is a convex function, but just for example, it's easier to start with something simple. We start here, then we move a little bit in the direction of the gradient, and now this is our new point. We move a little bit in the direction of the gradient, and we keep going down and down and down until we get to our minimum. On the left here, I've also just drawn it more in like 3 dimensions. You can sort of imagine gradient descent is sort of like dropping a ball in somewhere and then gravity pulling it down, but it's not necessarily a continuous process. We're more doing it in discrete steps. So what is this learning rate? So eta is some parameter, some coefficient that's greater than 0. If it was 0, then we just wouldn't do anything, and if it was negative, it would move us in the opposite direction that we want to be going. So we know it's greater than 0, but we don't want it to be too high or too low. If it is too high, then the issue that we run into is that we just sort of skip over the minima. So let's say we start here, and then our first step we move here, and then our second step we move here because eta is kind of high. Now this is a problem. We've completely stepped over the actual minima of the function, and now we've gone to a point such that the gradient actually points in the opposite direction. So now in our next step, we might jump back to all the way across the function, again stepping over the minima, and now our gradient points in the opposite direction, so we will be stuck kind of going back and forth and just missing the actual minima of the function. Now, if we make eta too low, we might eventually get there, but we're just going to get there really, really slowly. Every step will only move us a little bit, and so our gradient descent algorithm may not actually converge. Usually when you run gradient descent, you run it for a certain number of steps, and so that might not actually get to the point that you want it to get to. You can also run it until other sorts of convergence guarantees, but it will just take forever if your step size is too small. So another thing that we want to be careful of with gradient descent is we may need to do random restarts. Now in pink here, I've drawn a non-convex function. So if you start at this point, then gradient descent will get you to this, which is a local minima, but the true global minima is down here. So what random restarts is we're just going to run the algorithm, gradient descent, and then we're going to pick another random point, and we're going to run the algorithm there, and then we're going to pick another random point and run it again. And we'll take all the endpoints, and then we'll figure out which one of those minimizes the loss function, and that'll be our final answer. And this is helpful because now, even if some of your gradient descents get stuck in local minima that aren't global minima, you hope that at least one of your random restarts is in some region that will successfully fall into the true global minima of the function. And the last question, and sort of technique that we talk about in this class with respect to gradient descent is, doesn't this take a long time? Because the loss function L of W depends on all of the data points. Usually we assume the data points are independent, so it's going to be some product of probabilities, and then at every step in gradient descent, you're updating W, so then you're going to have to do the work of recalculating the loss function over all of these data points over and over again at every single step. And if you're doing a lot of these steps, this will take forever. And so this can often be true, especially on like really, really large data sets. And so in this case, we do what's called stochastic gradient descent. And that means we're going to use a random subset of the data points at each step. So we have our W, we pick some random subset of data points, we take the gradient at over those data points and our current value of W, and we move a little bit in that direction. Then we sample, we get another random set of data points, and we do it again. And depending on how many data points you pick, which is called your batch size, if your batch size is really small, then this will be really fast, but you're moving in a direction that might not be exactly your true loss function because you're only taking a small sample of the data points. And if you take a sample that's larger, it's going to be better at representing your true loss function, but it will take longer. Although, main benefit of this is that even if you use a batch size that's on the larger side, it's still going to be faster than using all the data points. And the second advantage is that this randomness can actually help us sometimes because it prevents us from being stuck in a local but not a global minima. So let's talk a little bit about how this happens. If we go back to our example non-convex function, we remember that under normal gradient descent, if we start at a point like this, we'll end up at a point like this, which is a local but not a global minima. However, let's say that we're doing stochastic gradient descent. So we're at this point right here, or some W around there, and then let's say that we consider some sample, random sample of the points, and under those points, the loss function actually looks something more like this. Well, under this loss function, since that's the one that we're using to calculate the gradient, we'll move largely in this direction. And then, let's say at the next step, we take a sample of points and our loss function goes back to looking something like our original actual true pink loss function, because that's what it'll look like under most samples. Now, we've already passed the hump that separates the local and the global minima, and so we'll probably continue to move in this direction and get to the true global minima eventually. So we see here that the randomness actually helped us. The possible difference between our loss function and our loss function under some small subset of the data actually was helpful in getting us to escape a local minima. This won't always be the case. Sometimes that randomness will actually end up hurting you, but there are cool ways in which that randomness can help you.